Let's take a second look at entropy from a microscopic point of view. In our first look at entropy, we defined the entropy as the energy unavailable to do work and related that to dq. From freshman chemistry, you might be familiar with entropy as a measure of the amount of randomness or disorder in the system. Both of these definitions are not altogether satisfying. In particular, talking about the amount of disorder or randomness in a system seems like a pretty fuzzy conceptual concept. Let's try coming at this concept of entropy from a microscopic point of view using what we know about energy levels and ensembles. To make our problem simpler, let's imagine a system consisting of three particles: a black particle, a red particle, and a blue particle. Each of these particles has 4 energy levels available to it. It can have an energy of 0, an energy of 1, an energy of 2, or an energy of 3. Let's constrain our system to be an isolated system with a total energy of 3. Now let's write out the microcanonical ensemble for this 3-particle system on 4 energy levels. In order for my total energy to be equal to 3, I can have all 3 particles with an energy of 1, or I can have 2 particles with an energy of 0 and 1 particle with an energy of 3, or I can have 1 particle with an energy of 0, 1 particle with an energy of 1, and 1 particle with an energy of 2. There is only one way I can make this state with all particles in energy level 1, and therefore this has a degeneracy of 1. However, there are 3 ways I can make the state with 2 particles in 0 and 1 particle in 3, because I can have the blue, the black, or the red particle with the energy level of 3, the other 2 having 0, giving me 3 possible ways to make this state, and a degeneracy of 3. There are 6 possible ways that I can make the energy state with the particles spread out on 0, 1, and 2. And so the last state has a degeneracy of 6. Using my fuzzy concept of randomness, I would designate this last system as the most random because my particles are the most spread out. The most organized system is the one with all the particles in the same box. And so we can see that the more random the system, the larger the degeneracy of that system. So we might expect that the entropy would be related to the degeneracy of the system. And in fact, we can relate the entropy to the degeneracy through the Boltzmann constant. The entropy is equal to the Boltzmann constant times the natural log of the degeneracy. So we can see with this definition of entropy that entropy is simply a way to count the number of microstates in the ensemble. The larger the number of microstates, the more entropy and the more random the system is.